Professor Kurdahi received the Distinguished Alumnus Award in recognition of his timely contributions to design automation of digital systems and reconfigurable computing and his entrepreneurial skills. He received his Bachelor's of Engineering degree in Electrical Engineering from IUB in 1981 and the Master's PhD degrees from the University of Southern California in Los Angeles in 82 and 87. And he then joined the Department of Electrical Computer Engineering at the University of California at Irvine. He has appointments in two departments, in fact, Department of Electrical Computer Engineering and Department of Information and Computer Science. For 2 years, from 2000 to 2002, he took a leave to found a company called Morpho Technology, and it was listed as one of the top 60 emerging startups in 2005, and it is being still Morpho. He is also a fellow of the IEEE, and he has published widely in his field of expertise. Please join me in welcoming Dr. Fadi Kurdahi.
So it's a pleasure to be here. I remember coming to this hall on my first ever day at AUB. We were taking a course, used to be called AS-011, which is now called CS, I think. So we came here, and I think we were studying about architectural buildings. In Lebanon, we had a professor from Germany, Professor Giesen. And he had an interesting way of taking roll call. He would actually, he got the TA to come in the first hour. He must have said something in the beginning, but I didn't listen to him, being a new person, all about AUB and everything. And so the TA would come in and in the first lecture, and he would kind of look at the seats, and he would, the next time, so who's sitting, next time if you're not sitting in your place, he would mark you as absent. So we, being Lebanese, the word is fawdawiyya. We come and sit every time different place. And so we would be marked absent, and we get some warnings about being absent from lecture and everything. So I learned, the first thing that I learned from AUB is to have to be at the right place at the right time. So now, I come from a same research domain that Professor Sakalla from, which is VLSI Design. And I was thinking of giving a talk on VLSI Design, but I think we wanted to have some diversity in the presentation. So I'm talking about a subject that we recently got into, that is taking some applications and trying to come up with platforms to support those applications. And one of those applications is the software-defined radio. I'm not an expert in software-defined radio, but I have worked in the supporting technology, which is called reconfigurable computing, that enables software-defined radio designers to realize their designs. So I'm going to start first by describing what is a software-defined radio. And essentially, a software-defined radio, by contrast to legacy radios, which is the kind of radios that we have. It's not a radio as in a audio, but it's a radio that essentially you find in your cell phone and anything that operates wirelessly. And a legacy radio, the function, as Dr. Hajj mentioned, defined in hardware. By contrast, a software-defined radio, the function is defined by software. In fact, to the operating parameters, things such as frequency range, modulation type, maximum output power, can be realized by software programming. Okay? So it is essentially a computer that generates, interprets, understands, and processes radio signals. Why do we need software-defined radio? Well, as you realize now, we're getting more and more different varieties of networks that we are exposed to when we move from one place to the other. At your workplace, moving to your favorite internet cafe, at home, outdoors, sitting inside your auto. If you're in a country where there is significant public transport, trains, buses, subways, all of these, you have to be able to seamlessly move your mobile device, whether it's a PDA, a cell phone, laptop, from one environment to the other in a seamless manner. So this poses some interesting challenges for the people that design those devices that will support these multiple types of networks. This is a photo from Nokia. The CTO, the Chief Technology Officer of Nokia, gave a talk at one of the major conferences some time back. And you can see here the important things. So try to see, find out where the, well, I'll use my finger. So you see here the different types of functionalities that are needed. You have the cellular modem here. You may need the radio the cell phone to receive or transmit FM signals, RFID, ultra-wideband, new technology for high data rate transmission, wireless LAN, Bluetooth, digital video broadcast, transmitting your favorite TV program to your cell phone, GPS, and so on. These are going to require different types of modems and also different types of antennas. So you have to decide on what kind of feature set to allow and what combinations would make sense of all of these. You have multiple standards. In the US, we have CDMA and GSM. You have 2G, 3G. You have to interoperate between them. You have also, most importantly, a very limited power budget. You have to worry about battery capacity, both standby and talk time, which essentially, as chip designers, would mean looking at power you consume during switching when you process the signal or when you're just sitting idle waiting for a call to take place. You have also cost constraints. You have to worry about development cost, how much time and effort it takes to develop such a platform, and of course maintenance costs. How much does it cost to upgrade? If you have bugs in the field, how do you fix them, and so on. So if I want to build an engine that is going to process these different standards, I have to understand how these engines work. And this is kind of a high-level view, if you like, of what happens when you take a signal from the antenna and you transform it into digital bits. What do you have to do in order to get to symbols that would be either voice or data or videos and so on? And so you have to first go through filtering. You have to do tasks like digital up-down conversion, decimation, compensation, match filter. Then you have to have the modem that will transform this into symbols. Typically, these are soft symbols. Will do these types of modulation schemes, and many others, of course, are possible. Then you have to compensate for the errors that occur when you transmit a signal over the air. So you have to do error correction, and there are different standards. These are complicated algorithms that will essentially try to correct as many of the errors as possible. And then this goes to the application layers. As I mentioned, could be voice or video or just plain data when you're browsing the internet. Now, what we know is that there's lots of common tasks between these different standards. In fact, if you look, there's a couple of examples here. 3 standards. WiMAX is a standard for broadband type of WAN, if you like. And then this is another standard that's similar to it. It's deployed in Far East. And another one, which is DVB-H for video broadcast. And you can see that they have lots of similarities. They use a lot of different kernel functionalities that are building blocks within each standard. Now, also, you have to be cognizant when you're thinking about putting these protocols together or covering them of how they interoperate. So, for example, you might be doing a call in a voice call, let's say, and at the same time, you might initiate a session browsing your favorite internet site. Or later you might be wanting to watch your TV program, and so on. So now, what we have to do essentially is to build a digital signal processing engine that can take input from these different standards which operate at different radio frequencies. This part, we really, being digital designers, is something that, and the technology on the RF side is today less flexible than what we can do on the RF side, is less flexible than we can do on the digital side. So people are trying to combine some of these RF interfaces together into flexible interfaces, but it's still lagging behind what we do on the digital side. And so what we want to do is have this digital signal processing engine that is capable of morphing itself across different standards. And if you look at it, what you really have to do is to implement these types of algorithms mentioned, I showed you before in the chain for a receiver, into this software-defined radio. Ideally, you want to do this using a language that is familiar to system designers. They like to write in MATLAB or C, and the closer you get to that level, the more easier it's going to be to develop applications that run on the software-defined radio. So, question is, well, why would you want a software-defined radio? If I were to build one modem, one type of receiver, I can do it much easily and much cost-effectively by building application-specific modules that do those functions and those functions only, and putting it on a chip. If I were to take a general purpose processing engine or something that can morph itself to do multiple tasks, it would be bigger and it would cost more. It would not be cost effective for a single protocol. However, when I start implementing multiple protocols, then I have to have application-specific modules for each one of those protocols laid out specifically or built specifically in that chip. And that starts to becoming less and less cost effective. And that's where having a programmable engine that can reconfigure itself to do these different tasks at different times can become more and more cost effective. So the question is, when does that become more cost effective? Well, it really depends on that mix of applications. But I can show you essentially what my colleagues at Intel have done some time back, where they ran this experiment by trying to build application-specific implementation or specific implementations for different protocols. And on the other side, using a reconfigurable engine or a morphing engine, if you like, that can change to implement these different protocols at different times. And they found out that up to 3 protocols, if it's less than 3, then you're better off implementing specific or dedicated engines to do these different applications. Whereas over 3, then the programmable engine starts becoming more and more cost effective. Okay? Of course, this is specific to their applications. If you take your another mix of protocols, then you might get a slightly different number. But the point is that at some point, you start seeing the benefit of having a reconfigurable engine. Now, also something very important happens as we start moving into more advanced process technologies to build those implementations on a chip. Today, the chips or the process technology that we use to build transistors on a chip is the power consumed in those engines is becoming more percentage-wise coming from standby power. So standby power is contributing a larger percentage of the total system power. And therefore, the smaller the size is of the engine, the less power it's going to consume. And therefore, that's where the colleagues at Intel also came with the conclusion that even power can be reduced by having this programmable engine actually implement those multiple protocols. Now, question is, well, why can't I use a regular processor to do those types of tasks? Well, if you look at estimates of how much processing power is needed to implement some of the standards here, well, some of them are reasonable in terms of millions of operations per second, 200 MIPS, even going to something like 7,000. It's still reasonable, but when you get to the more advanced types of processing requirements, you're talking about 13 billion operations per second. Now, assuming that you take multiple general purpose processors, you put them together, you have to worry about cost constraints, power consumption constraints, and so on. So clearly, you can see that using a regular processing engine is not the kind of thing that you want to do, certainly not for a handset. Okay? And so what we try to do is to find a better mousetrap. And if you look at, this is a slide from one of my colleagues at Berkeley, which compares something we call the energy efficiency. That is, how many milliwatts of power does it take to implement or to process 1 million operations per second. Okay? So obviously, the smaller that value is, the more power efficient my implementation is going to be. So obviously, if I want to implement something that is, the larger it is, the better it's going to be. So if I want to implement something that is hardwired, dedicated engine, I'm going to get the most bang for my buck, like we say. If I want to do something that's fully flexible, I would need a lot of milliwatts to generate the kind of processing power that I would need to implement the operations required for this kind of application. So somewhere in between here is where we try to be. We want to be flexible, but we want to also be able to be reasonable in the power consumption, or power consumption numbers. So that's where reconfigurable computing comes in, where it gives you an alternative between a hardwired custom that is inflexible and the power inefficient implementations using general purpose processors. So reconfigurable computing is a technology that has emerged. It's kind of a fuzzy name for different classes of engines, or if you like, methods of implementing this processing requirement. So field programmable gate arrays is one example of reconfigurable computing, where you can program individual gates and their interconnections at the very low level of abstraction to implement any Boolean logic function, the kind of things that Professor Sakalla showed in his presentation at the Boolean gate level. Of course, you can make the dedicated engine blocks somewhat more flexible by giving them some more parameters that can change. For example, a filter, you can program the coefficients, and so on. You can also use digital signal processors. Look at the most common operations implemented in applications like filtering or coding and so on, and add instructions to a general purpose engine to make it more power efficient. You can also take multiple processors, the kind of things that companies do today, Intel and other companies, by putting multiple cores to do operations in parallel. So all of these fall within what we call reconfigurable computing. And people have tried different flavors of this reconfigurable computing to implement different, for different applications. I'm going to show a couple of examples that we've worked on. And the first one is on the base station side. This is the towers where you handle multiple users. And the other one is for more of the subscriber side, where you essentially, we're using it, or it's targeted to be used in public safety applications. So this is one chip that we worked on with Motorola, which is now Freescale. It's called the MRC6011. And if you look at today's Intel processor, you have dual core and quad core. This had 6 cores. And I'm going to show you what's inside each one of these cores. And it is capable of doing 48 billion complex correlations per second. This is a complex multiplication, or 24 billion MAC operations per second. I'm going to skip a lot of the details and tell you what's inside each one of these 6 engines. Inside each one of these 6 engines this is a blow-up of one of them. And this is what we have developed that Freescale used in their chip. One of the things you realize when you're doing these kind of DSP operations is that it is similar in terms of the kind of operation you do, and you do it on different pieces of data. So instead of having processors that operate independently of each other, we try to tie them in kind of what they do. So we use something called the single instruction multiple data paradigm. That is, you send a single instruction to all the processors in one row or in one column. They do all the same thing, but they get different pieces of data coming in. So now, this is not the whole story. What you really have to do is to worry about how you control it. You need another programmable engine here that sequences through those instructions and sends them to the processors here to do the same operations. You need also a very versatile data memory because you need to provide the right data at the right time to these engines, both column-wise and row-wise. Sometimes you have to realize that this engine cannot implement all the requisite operations, so you have to augment it with some specialized kind of blocks that can do the operations, those operations more efficiently. And you also have to worry about interfacing. Data comes in streaming, so you have to process it fast or buffer it until you can process it without stopping the stream of data coming in from the outside. The other more important part is you have to program it. And programming such devices is always a problem. We already have problems debugging code for one processor, let alone having 16 processors running together. So what we had to develop is use a familiar tool chain, the GNU compiler, GCC, which is an open source toolkit. We augmented it with some special, what we call intrinsics. These are statements that you insert inside your C code that will essentially do a broadcast or a vector type of operations. You say for all the processors in one row, do an add and a multiply. Okay? And so what you do is you write your code, you put in those instructions for the array in the middle of the C code, and you sequence through them using the controller. So the controller implements the C code, runs the C code, and then whenever you see an instruction that says specific, that is not C code, it gets broadcast to the processors in the array here. Okay? So this has to be supported by a simulator, a debugger, and also a development board where you can actually experiment with these kind of operations and try to run applications and gauge the performance and so on. So our first task was to develop the basic engine for a 3G, a third generation base station, which is essentially what you need for a single user. This is what you need for a single user, which is a sequence of, this is essentially a more detailed version of the receiver that I showed you a few slides back. And so you have to, this is a complex device called the rake receiver. I'm not going to go through details. You have to do some data shuffling operations. And then you have to do correct for errors that are in the transmission channel. And then you have to put it all together. You have different types of data that you have to combine together. And finally generate symbols here, voice symbols that you can decode and generate actual voice coming out of it. So our task was to take all of this, which people were implementing using application-specific integrated or blocks, dedicated engines to do it, and implement it in software using this programmable engine that I showed you before, and essentially generate voice and have it come out. So essentially demonstrate a real-time operation on this engine. So the way we did that is, I don't know how many of you have worked in communication or in essentially with MATLAB, but we use MATLAB, which is a familiar language for people who work in this domain. They implement their algorithms in MATLAB. And then from that MATLAB code, which essentially assumes that your variables are floating point, you have unlimited precision, you have to truncate it into fixed point, where you have limited precision. And then we built a kernel library of the basic functions that are needed for these different blocks in the chain of the receiver. Those get mapped onto the RC array, the engine that has 16 DSP processors. And this is a loop of iteration where we try to tweak the performance, improve it, and eventually get it running on a simulator, and after that, running onto the actual hardware engine. What can you do? Well, as I mentioned to you, those engines are doing the same operation. So if you have a loop, like you see here, you want to do a summation from 0 to n of this cross product here, then what you can do is farm it out, essentially take the n here and divide it equally across the different units. You have to process it. So you tell all the units to do the same operation, but then you provide different pieces of data, chunks of data to each one of these units. And doing so, you can achieve a 16x speed up, for example, if you have all 16 engines doing that. So once we implemented this, we show you here how we can achieve real-time operation. In this standard, data comes in, or symbols come in every 10 milliseconds, you have a new batch of symbols come in, a frame. It's called a frame. And so as long as you can complete the processing before the next frame comes in, then you can achieve real-time operation. So what you see here is the cumulative time it takes to do each one of these tasks, starting with the receiver here, all the way doing the voice decoder, so to get voice out. And also you have to be transmitting and receiving at the same time. So there's also the transmit function. Now note that we don't actually process all of this and then switch to process the next one and so on. These loops are intertwined. What I show you here is the cumulative time it takes to do each part of each one of these boxes. Okay? Now also you can do the same thing for video transmission. Here's an example where you're actually transmitting a video and then you're receiving it or receiving another video. So you have to not only do the receiver, you have to do it at the higher data rate, 384 kilobits per second, and then you have to take the encoded video signals here and decode them to generate a video at the output. So again, you can see here that we can, this can also be done in real time. So once you take that for a single user, you can see how you can actually scale it up to a multiple number of users. This is the chip that I mentioned to you before that Freescale did, which has 6 of these processors. And by having 3 of them here, and then some extra processing there's a couple of DSP chips and then a network processor here, they can actually build a base station that can accommodate up to 128 or 144 users. And you can see here how we can morph between different protocols. You can do either voice or data or any mix of those. You can do high-speed HSDPA, or you can do edge and so on. And in fact, also this chip was used to implement WiMAX by other companies. So that was the first example, which we did essentially trying to commercialize a technology that was developed under government support. Eventually, I moved back to the university and we started looking at another type of application for software-defined radio, that is public safety. Especially in the US, there's been a lot of issues with catastrophes that would happen every so often. Things like hurricanes or train wrecks and so on, where you have to have different first responders. First responders meaning things like police, paramedics, coast guards, what have you, that have to come in and they have to communicate amongst each other to make sure that the right aid is delivered to the right place at the right time. And that poses some problems because any of these agencies all have their own communication standards, and it's very hard for them to intercommunicate. People often would have to for example, the police may have to actually carry 3 or 4 different handsets with them to communicate with different, the firefighters or the paramedics and so on. And so there is a need to actually develop a platform that can intercommunicate between those different types of first responders. Okay? You also have to worry about different needs at different times, and also be able to have reliable communication, even when other regular means of communication break down, like cellular infrastructure. Okay? The requirements also are not only to have voice, but to also have data. And that's needed for the next generation of communication equipment to support video transmission, for example, location, and so on. You have a lot of operational issues. You want to be able to operate whether indoor or urban or even rural, where it's far away from high-density communication or essentially towers, if you like. You have to have a different coverage area, whether it's a hotspot, a wide area. And we also have a little bit of work in the RF side. I'm not going to talk about that either. And the challenge here is that we don't want to handle just voice. We want to handle data. Voice, there is already existing standard for that. We want to handle just the high data rates. So we have developed a platform that is based on field programmable gate arrays. You see here, this is from a company called Xilinx. And then we have also multiple radios. In this case, we have 4 of them. And this is operating at 2.4, 4.9, and 5 gigahertz bands. So we have been working with the company that provides these, Xilinx, and other universities to build this platform. It enables multi-user OFDM support. A lot of advanced algorithms take advantage of the fact that we have a flexible radio, that to essentially morph between different requirements at different times. We also, that's where my contribution comes in mainly, is to utilize power management algorithms to extend battery life. One of the problems, as I mentioned, with reconfigurable computing is that it tends to have a higher power consumption than specific dedicated engines to do those tasks. We're also involved in doing field trials, working with various public safety agencies to test the deployment of these boards that we have described to you. So what are we doing on power management? This is one of the main problems. In fact, it was one of the main issues that actually limited the deployment of software-defined radio in the past. So what we are doing here is something that is not too different from what you do in your laptop computer, for example, whereby you design your laptop computer to operate under high load conditions. So you have a maximum frequency rating for your Intel processor on your laptop. And whenever you're plugged into the wall, you can process at a high frequency, but you consume the most power. Okay? In other words, your battery life, if you're not plugged into the wall, your battery life is going to drain fast. On the other hand, if you're not doing a high load of operations, then you can dial down the frequency and the voltage and extend your battery life. Okay? Now, in case of a radio, what you do, you typically design your radio to operate under worst case conditions. Okay? And then when you're operating under those conditions, you essentially have a high frequency and high supply voltage, but then you're consuming you're essentially using up your battery energy faster. Now you realize that when you design for a worst case condition, you don't operate. Most of the time you don't operate under worst case condition. In fact, we found out that probably 5% of the time, even less, you operate under worst case condition. So under those conditions that are less than worst case, you can actually afford to, and you measure it continuously, by definition, the way you build your receiver. You can monitor those signals and find out when you're not operating under worst case condition and start dialing down the frequency and the voltage, and therefore you can maximally extend your battery life when needed. So since you're doing this 95% of the time, then you can stand to save a lot of power in doing so. So how can we take this and implement it further? Well, if I do a blow up of the receiver and I look at how I implement it, I notice that most of the blocks that I use in terms of that consume the most power, that is, happen to be data buffering memories. You have to take data, process it, and then write it into the next buffer, and then the next engine takes it from that buffer and processes it, and so on. In fact, if you look at it, the wise people that comprise the thinkers, if you like, of the semiconductor industry have looked at the trend in the chips that are being used in almost every domain. And they saw that the percentage of memory on those chips keeps increasing steadily to the point where they say about in the next few years, you're going to be getting upwards of 90% of your chip is going to have memories on them. So that's where we're concentrating to basically try to reduce power. Okay? Now, the other interesting part of this is that those data buffering memories, the telecom designers assume the worst. In other words, they say, I'm going to get errors coming from the channel, and I'm going to build a whole infrastructure in my engine to compensate for those errors. So they build in these forward error correction algorithms to essentially redundant, so data is sent redundant. In fact, when I send a 0 or a 1, a digital symbol of radio, it gets actually converted to an 8-bit or a 6-bit signal. And that's how it gets processed all the way until the very end of the receiver. So I have essentially 6 bits to represent a 0 or 1. Okay? So I have a lot of redundancy. Now, if you look at it, if I take this memory and I reduce the voltage on this memory, I want to save power. That's the only thing I can, it's the most powerful thing I can do to these devices. If I do that and I keep doing it aggressively, reducing it more and more, this memory is going to eventually exhibit some faults. And what you have to do, so typically people stop before that point. What we're doing is we're saying, let's be aggressive and let's keep reducing the power further and further by reducing the voltage. And then I'll start getting errors. But the data stored there has a natural resilience towards errors. So what we try to do is to try to use the existing processing algorithms in the receiver to compensate for those errors. Okay? So that's essentially what we do, the slack and the redundancy to compensate for those errors. Now we tried this on a system like this where we actually have video coming in and you encode it, you essentially transform it into symbols that can actually be transmitted over the air, you receive it, and you decode it and you get a video out. And we try to do this for both the wireless receiver and the video decoder. And so this is what you get. If you go into the worst case condition, you consume that much power, and you get a perfectly good video to watch. If I go in and aggressively reduce the voltage to reduce power, I can make a lot of power reduction, 40%. But then I get a video, because of these errors, I get a video that looks a bit grainy and it's hard to watch. So what we do is we keep track of where these defects have occurred, because these errors are reproducible. And you go in and fix them one by one using simple filter. For example, if you look at this pixel here, the neighbors, it's going to be most likely similar to its neighbors. So I go in and do something very simple called the median filter, look at the neighbors, and the average of those neighbors is what you assign to this faulty pixel. And you get almost a perfect video on the output. This costs you a little bit of power, but you still save quite a bit significantly in the overall scheme of things. Okay. Now, this solves one of the problems, but of course, software-defined radio has many, many other challenges, and there's still a fertile ground for doing a lot of research in this area. You have to worry about security. How do you reconfigure over the air? How do you essentially change the protocol when needed? How do you secure that? There is no standard today. How do you standardize these platforms? You have to also, as I mentioned, worry about the antennas, the RF front ends, and so on. There's many, many other challenges. Of course, the most important one is really how do you program those devices? And that's essentially what computer scientists are helping us to do by handling compilers and programming paradigms to better take advantage of the platform. So I part with some final thoughts. As I mentioned, software-defined radio is a very promising technology. We still have many challenges. Challenges are not only technical, they're also financial and political, and at the user levels. And however, the benefits and the payoffs are extremely lucrative. So I'll acknowledge also my many collaborators and companies and agencies that have funded our work. So thank you for your attention, and I'll be happy to answer questions.
Thank you, Fadi. I see One person wants to ask a question, Zahir.
Thanks. I have two questions. One is general. Is the bottleneck for software-defined radio really in the RF part, or is it in the signal processing and the baseband part? And the second, more technical question is about this power management scheme. You said that you want to make use of redundancy in order to reduce the voltage and have errors in the memory. But this seems to contradict the current state of the art of these wireless technologies, because when the conditions are good, the transmitter will not send you redundancy. I mean, current technologies, I will not send any redundancy if I have good conditions. So how does your scheme go along the current state of the art in wireless technologies?
So let me answer the first question. There are challenges on both. In fact, there are people that are working on flexible RF. One of my colleagues is essentially developing this dual or tri-band type of RF, but it's hard to make it almost continuous, so the cost becomes higher. Part of the cost is also the analog to digital converter. I mean, it depends on how you do it, but that could become actually the bottleneck there. There's also challenges on the digital side. Many of these programmable engines still have some application-specific accelerators for doing some of those functions. Hardest ones would be something like the turbo decoders or other forward error correction schemes. Now the second one, you're right. There is adaptivity, and what we try to do is either make the designers. So our point is the following: that today you have the people that design the chips and the people that design the telecom system. There's a wall between them. The people that design the telecommunication system design it in MATLAB, maybe get a C code, and then they throw it over the wall. And these guys, all they know is that they have to implement this. What we're trying to do is to make the system designers aware of the capabilities and shortcomings of the digital side. One example of that is to give them a table that shows percentage of errors in the memories as a function of the supply voltage, and give them a capability of doing a rough estimation of power consumption under different conditions. Now, having a software-defined radio platform helps them see what the structure looks like. And so when they have that, they can compensate for it. For example, one way to correct errors is to do turbo decoder. A turbo decoder, you essentially try once, and then you try again, and you keep doing that until you get almost no improvement. So the telecom system designers, if they're aware, if they want to do some power trade-offs, they maybe decide that when I reduce the voltage, I will try to increase the number of iterations, or maybe increase the memory that sits between the decoders that bounce data back and forth between them. And therefore, you can get a lot of benefits. So it's not just take a system and then make it blindly do those voltage reduction, but have that information available to the system designers so that they can essentially use that to their advantage. They are the ones who can make the most difference in the design.